All right, so what I want to talk about now is an important generalization of the monotone convergence theorem. And besides being very practically useful, it maybe more importantly introduces a philosophy that we're going to take throughout the rest of this course on these theorems where you interchange limits and integration. In general, we're going to take this philosophy here that sets of measure zero don't matter. Okay, so what do I mean by that in this context? Well, let's say we're in the same situation as a monotone convergence theorem. So we have a sequence of monotone, increasing, not necessarily strictly increasing, but increasing functions that are non-negative and measurable. Okay, now let's say we have some function e where f of x is this pointwise limit almost everywhere on e. Okay? And as we mentioned when we discussed the monotone convergence theorem, this limit actually exists for all x and e. It could possibly be infinity, and in fact, if it happens that for some integer n, fn of x is infinity, well, fn plus 1 of x is bigger or equal to fn of x, so fn plus 1 has to be infinity. Fn plus 2 of x is bigger or equal to fn plus 1 of x, so fn plus 2 of x is infinity, etc., etc. So, if fn of x for any n is infinity, then the limit will be infinity. It could happen that this limit is infinity for every single x. That's okay. Regardless, this limit does exist as either a real number or plus infinity. So the claim is that f is measurable, and this integral is the limit of these integrals. So the point here is that f of we don't care about a set of measure zero where this possibly is false. And we've seen, little bits and pieces of sets of measure zero don't matter here and there throughout this course, but it's really going to be important going forward. And this is practically useful. A lot of times in applications, you don't have convergence on a set of finite set, but just knowing that you have this flexibility of not caring about convergence to f of x on a set of measure zero is really, really useful. It's really nice. And I'll do a concrete example of this after I prove this. So what's the proof? Well, as I mentioned, this limit here exists for all x and e. It could be plus infinity. That's okay. Regardless, we know from chapter 3 that the pointwise limit of measurable functions is measurable, and that is, what is that? That is proposition 9 on page 60 in the book. And I claim that because f equals f tilde almost everywhere, that f itself has to be measurable. Okay, why is this true? And this is a pretty easy thing to prove. Basically, problem 2 in the exam was very similar to this. So let's say A is a set of all x where f of x is not equal to f tilde of x. Well, remember f tilde is this limit, and the assumption is that this limit equals f of x almost everywhere. So f tilde of x as a limit equals f almost everywhere, so A has measure zero. We know sets of measure zero are measurable. And what literally was part of the second exam problem was that every function on a set of measure zero is measurable. So f restricted to A is measurable. And that's basically, I'll put up the exam problem soon, but that's basically trivial because every subset of a set of measure zero is measurable, because every subset of a set of measure zero also has measure zero, and hence is measurable. There's not a whole lot to this. Okay. Now again, we know that f tilde is measurable. So f tilde restricted to E take away A is measurable because E take away A is measurable. A is measurable, E is measurable, so E take away A is measurable. So I mean, implicitly in all these theorems, of course, as I've mentioned numerous times, E is measurable, even if I don't say it. Okay, so we know because f tilde is measurable, a measurable function on E, and E take away A is measurable, we know from proposition 5 on page 56 that f tilde restricted to E take away A is measurable. But on E take away A, f of x is f tilde of x. Why? Well, there's nothing to that. If we're away from the set of all x and E, where f of x is not equal to f tilde of x, but we're still in E, then f of x equals f tilde of x. So these two are literally the same function. So f restricted to E take away A is measurable because it is f tilde restricted to E take away A. Okay, so we're going to use proposition 5 on page 56 one more time. In fact, because A is measurable, and f restricted to A and f restricted to E take away A is measurable, these two being measurable implies, by proposition 5, that f itself is measurable on E. Okay, so f is measurable, and so there's no ambiguity on this integral. It makes sense. There's, yeah, f is measurable. Okay, now by the monotone convergence theorem, because f tilde is the pointwise limit of these fn's, the integral of f tilde of x is this limit here. On the other hand, it's an easy homework, really not a whole lot to this. I will assign this to be due on Monday because it really is pretty damn easy. The fact that f tilde equals f almost everywhere says that these two integrals are equal. Okay? And that finishes the proof. And actually, I should be a little more honest. Recall that we didn't really need f measurable to define the Lebesgue integral of a non-negative function. It was just that none of the theorems, none of the useful practical theorems that make integration make sense hold. You really can't prove anything about integration unless you're integrating a measurable function. So that's why we really want f to be measurable. Otherwise, you don't know anything. None of the properties that we proved for this integral are true unless f is measurable. So even though strictly speaking, you do not need measurability to define the Lebesgue integral of a non-negative function. Okay. Yeah, so that takes care of the proof. All right, and the same proof that we just went through proves, and I'm not going to make, I mean, this is good homework if you have any doubts. I'm not going to collect it because it literally is the same proof. If you have two extended valued functions that are almost everywhere equal on E, then f is measurable. One is measurable if and only if the other is measurable. Right. Okay. So let's get to an example. Okay. And so we've already seen an abstract kind of example of using the monotone convergence theorem to prove that if you have a sequence of non-negative measurable functions, that you can interchange infinite sums and integrals. That was in the previous video. And it's a really beautiful application of the monotone convergence theorem. It's very important to know that you can interchange sums and integrals of non-negative measurable functions. But let's look at a more concrete application of this more general monotone convergence theorem. And that is let's compute this Lebesgue integral for alpha positive. So you can check if you so desire. This is a measurable function. And yeah, and so it's measurable. Well, so certainly this Lebesgue integral is going to exist. This is non-negative, this function here. It is infinity when x equals 0, but that's okay. Okay, so yeah, so how do we do this? Well, we're going to truncate this function here in kind of the obvious way. Well, I mean, not necessarily the absolute obvious way, but there's a million ways you can truncate it. Let's do the simplest thing. Let's just basically let fn of x be x minus alpha, except it's 0 if we're between 0 and 1 over n. But otherwise, let's say it's x to the minus alpha. Okay. So clearly, point-wise, this is going to be x to the minus alpha as long as x is not 0. Okay. And that's pretty trivial because if x is strictly between 0 and 1, including 1 possibly, then certainly x is in 1 over n to 1 for large enough n. Okay. And as n gets larger and larger and larger, it stays there. So so the limit is just x to the minus alpha, because fn of x is x to the minus alpha for large enough n. On the other hand, no matter what n is, you plug in 0 here, fn of 0 is going to be 0. Okay. No matter what n is, 0, if x is 0, no matter what n is, 0 is in 0 to 1 over n. So fn of 0 for every n is 0. Okay. So this illustrates, why we want flexibility with convergence pointwise. We don't have convergence pointwise to x to the minus alpha for all x on 0 to 1. We have it for certainly almost all x between 0 and 1. I mean, the only issue is x equals 0. But that's okay. I mean, certainly a set of singleton is a measure of 0. Okay. So because this function here is 0 on 0 to 1 over n, this integral here as a Lebesgue integral just becomes 1 over n to 1 of fn of x. And fn of x is x to the minus alpha on 1 over n to 1. This is a perfectly nice continuous function on 1 over n to 1. So we know the Lebesgue integral coincides with the Riemann integral when functions are Riemann integrable and continuous functions are Riemann integrable. And we can compute this Riemann integral, well, just by the fundamental theorem. So in particular, if alpha equals 1, hopefully you remember the integral of x to the minus 1 is ln of x. So it's ln of 1 minus ln of 1 over n, which just properties of ln becomes ln of n if alpha is 1. And if alpha is not equal to 1, but it's still positive, well, either way, just alpha not equal to 1, you just use power rule. You're integrating x and minus alpha, so it becomes x in a 1 minus alpha over 1 minus alpha, plug in 1 over n, and just fiddle around a little bit. You get this right here. Okay, just literally Calc 1 fundamental theorem. Okay, so the monotone convergence theorem tells us that because fn converges to x to the minus alpha almost everywhere on 0 to 1, again, the only problematic point is 0, and certainly a singleton has measure 0. We can use this generalized monotone convergence theorem, and we can compute this integral, which we calculate, this limit here. We just calculated this integral right here. And you can see that unless alpha is between 0 and 1, we get infinity. So we're just recovering the Calc 2 fact that we all hopefully kind of vaguely remembered. But the point is that, this is how we would carefully compute this Lebesgue integral using the monotone convergence theorem. Okay, and another interesting thing that you absolutely took for granted in Calc 2 is you'll notice that there's nothing special about 1 over n here. I could have put, instead of 1 over n, I could have put e to the minus n. I could have put 1 over n to the n to the n to the e to the n. It doesn't matter how I truncate this function here when I'm doing this. Okay. So this actually proves, if you think about it carefully, this Calc 2 fact that we implicitly used, that it doesn't matter how I truncate these integrals when I do these improper integrals. And the monotone convergence theorem basically tells us that carefully. No matter how I truncate here, I'm still going to get almost everywhere pointwise convergence. Okay, no matter if I put 1 over n, 1 over n squared, et cetera, et cetera. So, right. Okay. Right. So what I want to do now, so we're going to finally get into the general Lebesgue integral, and really all the hard work is done already. We have one last deep theorem to prove. Even then, it's really a consequence of the Fatou's lemma, and that is the Lebesgue dominated convergence theorem, which is, I would say, well, I'll put all three of these theorems in perspective. Fatou's lemma really should be its theorem, but I guess because it's used to prove the dominated convergence theorem, and we use it to prove the monotone convergence theorem, it's called a lemma, but it really deserves to be called a theorem. But yeah, I'll put into context the three big theorems: Fatou's lemma, monotone convergence theorem, and the Lebesgue dominated convergence theorem. Really, when combined, these three are it, except for some very, very, very special circumstances. They basically are it when it comes to when can you interchange integrals and limits. All right, so what I want to do is a quick complex numbers review, because, well, we're going to do the general Lebesgue integral for complex valued functions, and that's not just academically, it's not just an academic exercise, particularly for the Fourier transform and Fourier series. We absolutely want to integrate complex value functions. And you don't get more applicable than Fourier transform and Fourier series. In general, there's no reason not to, take on this generality. I mean, if you want to apply Lebesgue integration theory to other areas, like number theory, you really do need to deal with complex valued functions. All right, so what is a complex number? I'm going to go quick because I presume everyone has seen complex numbers somewhere, somehow, in some way. It's just a number of the form x plus iy, where x and y are real, and I squared is -1. In that regard, everything else is basically the same. And we usually refer to x as the real part of z and y as the imaginary part of z. Okay. So the modulus of z, which I sometimes call the absolute value of z, is the length of this z considered as kind of a vector in the plane. So it's square root of x squared plus y squared. And we call it r because it is the r in polar coordinates if you consider, again, x, maybe not so much as a vector, but as just a point. If you consider z as like a point xy in the xy plane. Okay. And so that consideration leads us to the polar form of a complex number. So first of all, what does it mean for z to be 0? Well, just like it, what does it mean for xy and the xy plane to be 0? It means both x and y are 0. This is no different. Z equals 0 means x equals y equals 0. That's the same thing as saying the absolute value of z is 0. The only way this is going to be 0 is if both x and y are 0. Otherwise, it's positive. Okay, so what is a polar form of a complex number? And I'll throw up a picture in a second. Well, it's writing z in the form of r times alpha, where alpha has modulus absolute value 1, and r is the modulus absolute value of z. And there's not a whole lot to this. So let's just take x and y, put it in the xy plane, and put it in polar form. And we know, we better know, that that's r cosine theta, r sine theta. Here's the picture. Okay. And r, again, is the length of this xy, thinking of it as a vector in the plane, or just the distance between 0, the origin rather, and x and y. Okay. So in polar coordinates, right, this is r cosine theta, r sine theta. Well, if we translate xy into x plus iy, we can translate r cosine theta, r sine theta into r cosine theta plus I r sine theta. And we can factor out an r to get r cosine theta plus I sine theta. And you should check, it's really nothing, check that this, no matter what theta is, has absolute value of 1. I mean, here, it's just cosine squared theta plus sine squared theta square root is 1, because cosine squared plus sine squared is always 1. Okay, so right, this is really just polar coordinates. Okay. So let's look at an example. Let's write 1 minus I in polar form. So actually, I'm emphasizing polar form because that's something we're going to need to use in the next video. Okay, so right, in this example, we're just going to figure out the polar coordinates for 1 minus I. So we have this point 1 minus I. So r is just, well, x squared plus y squared square root. So that's square root of 2. So let's figure out what this angle is. And remember, tangent theta is y over x, polar coordinates. Y is minus 1. X is 1. Y is the imaginary part, which is minus 1. X is the real part. And so theta is minus pi over 4. Tangent, if we have something in the fourth quadrant and the tangent is minus 1, that corresponds to an angle of minus pi over 4. Okay? So, right, so that means z is, again, r cosine theta, I r sine theta, which is square root of 2, cosine pi minus pi over 4 is root 2 over 2. Sine minus pi over 4 is minus root 2 over 2. And then we factor out the r. And right, that says that z is r times this alpha here. And you can directly check very easily that this has absolute value of 1. If you square root 2 over 2, you get 1/2. You square minus root 2 over 2, you get 1/2. 1/2 plus 1/2 is 1. Square root of 1 is 1. Okay, so a concrete example of putting a complex number in polar form. All right, so how do you multiply complex numbers together? Well, you just multiply them together, usual FOIL, just taking into account that I squared is minus 1. Okay, so right. So what are we going to do? We're going to well, let's multiply x1 by these two first. So x1, x2, that's right here. Then it's x1, I, y2, which I write as ix1, y2. Then I'm going to do iy1, x2. I stick the x2 in front. Put the x's in front. Just looks a little nicer, I think. And then we're going to do iy1, iy2. Well, I times I is -1, so it's -1 times y1 times y2. And we just get this into the form something real plus I something imaginary. Well, in the imaginary, we have an I here and an I here, so it's x1, y2, and then x2, y1, and then here it's x1, x2, minus y1, y2. Okay, so in practice, of course, we don't memorize this abstract formula here and apply it. We actually just do this. So as an example, let's multiply these two numbers out. Okay, so we're going to do exactly what we did. Let's first do let's do 1 times 2 minus I, and that's going to be 2 minus I. Let's do the 3I times 2 minus 1. 3I times 2 is 6I. 3I times minus I, well, I times I is -1. Minus minus is plus, so it's going to be plus 3. Okay. So it's 2. 6I minus I is 5I. Plus 3, 5 plus 5I. And I forgot to mention, though it's fairly obvious, that you add complex numbers in the obvious way. You add the real parts. Then you take I times adding up the imaginary parts, just like we're doing here. So there should be no ambiguity with adding up complex numbers. And again, hopefully this is a review. Okay. Right. So what's next? Well, let's look at complex conjugation. So if z is x plus iy, the complex conjugate is z minus iy. And this is very important. Well, in general, it's extremely important. But for us, what's the point? The point is that you can multiply z and z bar. Let's see what this is. You probably know the answer, but it's going to be x squared. Okay. X times minus iy is minus ixy. This is going to be iyx is ixy. Okay. And then I times I is, well, let's just do iy times minus iy. Well, I times I is -1, minus minus is positive. So this is going to be positive y squared. These cancel. So it's x squared plus y squared is modulus c squared. Okay. And this is extremely useful because this allows us to define what 1 over z means. Okay. So it might not be immediate. What does 1 over z mean? I mean, like 1 over 5 makes sense. It's just 1/5. 1 over 5, like 1/4 is, I mean, it just makes sense. Even 1 over 1 over e kind of makes sense, But what is 1 over a complex number? Well, we're going to define it using this complex conjugate. So z to the -1, really 1 over z. We're going to define it in this way. So it seems a little silly, but the intuition here is obvious. And I want to emphasize we're defining it this way. We're defining 1 over z, same thing, z to the -1, as this here. The intuition is clear that the z bars cancel out. Okay. But there's no wishy-washy ambiguity here. Z bar is x minus iy. Z bar is x squared plus y squared. So we have a perfectly well-defined, concrete, complex number called 1 over z. Now, of course, if z equals 0, we don't define this. Okay, so one thing to check is that z times 1 over z actually gives you 1. That's the same thing as z to the minus 1z. I don't know why this z ended up looking like an exponent, but this is z to the minus 1 times z. So z times z to the minus 1 equals z to the minus 1 times z equals 1. And you can check that very easily. By definition, well, z is x plus iy. Z to the minus 1 is x minus iy, x squared plus y squared. So when you multiply the two together, just bring z into the numerator. We get this here. Well, this is z bar. So you just get 1. So not very deep, but. Okay, another thing to note is that the modulus of z to the minus 1, well, this is the real part, x over x squared plus y squared, so you square it. The imaginary part is minus y over x squared plus y squared, so you square that. You can check with a tiny bit of algebra that this is going to be modulus z squared over modulus z to the fourth. I mean, it's pretty obvious. You have the common denominator, x squared plus y squared, whole thing squared. And, you know, you're going to get x squared from here and positive y squared from here. Well, inside the square root, that's going to be 1 over modulus z squared. Square root of that is 1 over modulus z. So as you would hope, modulus z to the minus 1 is the modulus of z to the minus 1 is the modulus of z to the minus 1. Okay. All right. And it's a homework, and it's a little messy. You have to compute, but you can check it. I really won't collect it, but if you do have any doubts about complex numbers, do check this yourself. That the modulus of z1 times z2 is modulus of z1 times modulus of z2 for any two complex numbers. And in fact, this note here follows from this. If z1 is z and z2 is 1 over z, because that's just saying, well, you multiply the two together, you get 1, and that would be modulus z inverse. So modulus z inverse is the inverse of modulus z. Okay. All right, so one last concrete example before we end the video is, let's find 1 plus 3i times 2 minus I to the minus 1. All right, well, let's get 1 over 2 minus I first. Again, so I'm not sure if I would memorize the definition. What I would probably do is remember, just multiply top and bottom by z bar to get 1 over z. So, I mean, to compute 1 over z, multiply top and bottom by z bar. So it's z bar over z bar. So I guess that's the same thing as memorizing the formula. But anyway, so z bar, the imaginary part here is minus 1. So z bar has imaginary part plus 1. So this is 2 plus I over 2 minus I, 2 plus I. 2 plus I in the numerator stays. This is, you can either remember z bar is modulus z squared, or just distribute this out. You get 5 either way. 2 squared plus minus 1 squared is 5. Okay, so that's what 2 minus I to the minus 1 is. So now we just multiply these complex numbers, bring out the 1 over 5, distribute just like we did before. Distribute the 1, it's 2 plus I. Distribute the 3i, 6i. 3i times I is minus 3. So inside here, it's going to be 2 minus 3 is minus 1. 6i plus I is 7i. Divide by 5, minus 1 over 5 plus 7i over 5. Okay, so actually, two more things before we finish up. An easy homework that you can check yourself if you so desire is that the triangle inequality is true. Actually, if you've taken advanced calculus of several variables, I forget what 400 level course this is at SUNY Albany, but this basically follows immediately from the fact that the triangle inequality is true for numbers in Euclidean space, Rn, because the absolute value of x plus iy is the norm of xy as an element of R2. So this fact follows immediately from that. But you can also prove this yourself if you so desire. And second, this I might collect. So what does it mean for a sequence of complex numbers to converge to a complex number? Well, it means exactly that this limit here is 0, and there's no ambiguity here. Modulus zn minus z is non-negative. So Zn converges to Z if, well, as n goes to infinity, Zn gets really, 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 really close to Z. That's quantified by the statement here. And a homework that, yeah, I might collect. Again, you did prove this essentially in advanced calculus of several variables if you took it at SUNY Albany. Yeah, so if Zn is xn plus Iyn, and if Z is x plus Iy, then Zn converges to Z if and only if both xn converges to x and Yn converges to Y. All right. A very easy homework, but anyway. All right, so hopefully this little quick review has been useful. We're not going terribly deep into complex numbers. If you're enamored by complex numbers, I definitely recommend you take 513A. I don't know who's teaching it in the fall, but that's a course on doing calculus with complex valued functions. And it's really beautiful stuff because just the fact that we're doing calculus involving numbers, sorry about that. Where did it go? So just the fact that we're doing calculus with numbers that involve this imaginary I squared equals -1 number changes the theory of calculus drastically in completely and utterly unexpected ways, and you get an absolutely beautiful and much deeper theory than ordinary regular calculus. That's actually very useful in real life. That's again 513A. Very, very interesting course. Okay, so long. Take care, stay safe, stay calm, and let's all be more like this guy here and super happy and cheery and whatnot. All right, and I'll put a video up on the general Lebesgue integral pretty soon.